Hello everyone, welcome to Gyandeep, a channel where we talk about everything that relates to data science. Okay, so here in this video session, we are going to talk about one of the Kaggle competitions which is currently underway. It's called Feedback Prize English Language Learning Competition. It's in fact the third in the series. There were two other competitions along similar lines which happened in the past. The goal of the competition here is to assess the language proficiency of 8th to 12th grade English language learners or ELLs. We are provided with an ellipse corpus, right, which comprises the argumentative essays written by the 8th to 12th grade ELLs. And the essays have been scored according to the six analytic measures, which are cohesion, syntax, vocabulary, phraseology, grammar, and the conventions. For each of these analytic measures, the students get a score ranging from 1 to 5, and it increases in the step of zero point 0.5. So the score could be 1, 1.5, 2, 2.5 for all these six different measures. Our task is to predict the score of each of these six measures for the essays given in the test set, right? Now, here our ultimate objective is to build a baseline deep learning model and understand the nuances of it well so we can lean on it and build the more advanced model. Okay, so now let's take a closer look at the data. I've taken this snippet from the train.csv or the training file that has been provided. So it has got the 8 different columns. I've got the text ID, the full text, and then the 6 other columns, which are the part of the predictions or the labels, I would rather say. Right? So we have cohesion, syntax, vocabulary, phraseology, grammar, and the conventions. Now, these six of the classes have to be predicted from the full underscore text or the corpus, which is here. Let's try to understand how the corpus actually looks like. I have taken a sample full text here. So if I read it for you, it says, I think that students would benefit from learning at home, comma, because I think this essay would have required the student to talk about the benefit of learning at home. Okay, that's my guesstimate. Okay, now here in this case we see that home, comma, because there is no space here, so I'm assuming this gets captured as the single word, right? They won't. Now there's no apostrophe here. Similarly, if we go further, the use of there, it should have been THEIR, but it's here presented as THERE. Similarly, I encountered several of the grammatical syntactic inconsistencies in this particular essay. So basis that this essay has been scored and it gets a cohesion score of 3.5, syntax of 3.5, and so on and so forth as we see the score here. Okay, now we have to use this data and predict for these six different classes as we understood earlier. Let's now get into building the model. There are several steps involved into building the deep learning model, which would predict for these six different classes using the corpus that we saw earlier. We'll start by first importing the libraries. So we will essentially try to understand why those libraries are needed, right? Then we'll go about loading the data. We'll define the config basis which will have the pre-trained model and so on. Then we'll have the dataset class. We're using PyTorch here. We'll then define the model architecture and then we'll have the trainer which will essentially fit on the model architecture that we would have defined in the previous bullet point, and will optimize for the loss, right? And Then we'll have the evaluation of the model done, and finally we'll have the inference notebook as well, where we get the predictions on the unseen data. I will be covering all this in three different videos. So maybe till model architecture, I intend to cover in this video session. The trainer and training the model and evaluation, those two bullets will be part of the next video session, and inference, I will have it covered in the third video session. Let's get started with the coding part of it. I already have the Kaggle notebook in front of me. I have made use of some of the code provided by our Kaggle fraternity itself while recording or while building this notebook. And I must say that I have benefited a lot during the process. So I just wanted to talk little bit more about the notebook itself. I'm using GPU P100 here. So recently Kaggle gave us the option to have the another version of the GPU as well, which is T4X2. When you actually start the notebook from the competitions page itself, then it comes preloaded with the data, and that's why I already have the sample submission test and the train.csv here. So let's get started by importing the libraries. So essentially we have to read these three CSV files. So I definitely need the pandas. So I will be importing the pandas as PD. We import the OS. I need the transformers, and we'll be importing the auto model and the auto tokenizer. This will help us because for whatever model that we pre-trained model that we want to use, will not have to worry about getting the same class of the tokenizer. It will automatically get the same for us. We'll be then importing the torch. I'm using torch here. We will get the NN module of the torch. And then we'll also be importing numpy as np. We'll be splitting the train data, this particular train.csv, and for that purposes, we'll be using the train test split function under sklearn. To track the progress of the model building, we'll be using tqdm. And then once we have the modeling done, and when we need to evaluate the losses for the train and the validation, we'll make use of matplotlib.pyplot, and essentially to see a visual representation of how the losses compare. We'll use GC to collect the garbages and free up the memory. Okay, so let's get started with loading the data. Train, here we load the data. I can directly get the path from here. So copy file path as you see, and we can read the data from here. So I already have that for you. And so we have train, test, and sub data. Let's quickly see how the train data looks like. So just a small sample of it here. Train.head2, which gives us text ID, full text, and the 6 other columns as we saw earlier. Right? So now let's come to this part where we define some of the parameters or config that we'll be using throughout the notebook. Right, so in this case, I'm using BERT base uncased. You are free to use any other BERT or the similar models like DistilBERT or Roberta or any other different form of the BERT that you might be wanting to. That could be the part of your next level experimentation. Now, while we are connecting the hidden layers, and while we are uh, uh, allowing the model to actually learn from the data patterns, we want to avoid overfitting, and we want the memory, some part of the memory to leak out, right? And that's where the dropout will be useful. Right now, I have kept it as 0 dot, which means it will be undertaken as a float value. The max length is defined to be 512, which is the maximum number of the tokens that the bird would get applied on this model essentially would be receiving at max 512 tokens, which means that if certain text is less than 512, then in those cases we'll need to sort of put in the padding for the same, and those cases where it is more than 512, it will get truncated. We will run the model or we'll train the model for 4 epochs, and we'll see how it fares in terms of accuracy. We'll take a batch size of 16. These are all experimental, and we can see. And we'll be talking about freezing the learning rate and so on. The one of the best thing to do is to freeze the learning rate, and when we get into the trainer part of it, we will get into this part in little bit more detail. Now the device is defined to be CUDA if torch.CUDA is available, which means that the device currently will be running on GPU P100. Otherwise, if this gets exhausted, then it will go on CPU. When we get into the trainer part, we'll also talk a little bit more about scheduler here. We'll be using cosine annealing restarts, which functions in a little different way than the typical scheduler that we use, which is reduce, LR, plateau. So we'll talk about it again when we are in the training phase of it. Okay, so once we have defined some of the config related parameters, then we have to create the feedback dataset class. Okay, so this we initialize it by def in it, and the arguments here could be the training data frame, the config. In this case, the tokenizer is none, and we want to give the argument for is test or not. So in this case, since we are trying to train the model, we'll have it as false. Self.df, so we in this essentially gets the value of df. We reset the index and drop any index that might have been there as part of the column. Next, we get the classes. Here, there are 6 different classes that we saw earlier: cohesion, syntax, vocabulary, phraseology, grammar, and conventions, which we have put in as the list. And the max length, like we saw earlier, it's 512. Tokenizer is tokenizer. The is test is this test. Now we will identify we'll write the function to identify or get each of the item row wise. So we'll give the idx, which is nothing but the row number, right? So the sample in this case would be self.df full text idx. So essentially this will give me, so if idx is essentially 0, right, then it will give me the first row and under the full text, right, that particular column. So that way my sample is defined. I will keep on getting the text here, and now we'll have to tokenize this text, right? Whatever the string or the text that we get. The tokenized, so we create here a variable now, which is tokenized, tokenizer. We take the tokenizer and we are using here encode plus. Encode plus will takes, you can use help actually to see as to what encode plus will take as the argument. So if you just do help and put in the bracket the tokenizer dot encode plus, then it will give you the various arguments that in this particular function would be taking. right? So in this case, it takes the each item. So we are giving the sample here, which is the individual or row wise the full underscore text. Then it also accepts the text pairs. We are not giving any text pairs here. Then we can add these special tokens. So this gives, so we are putting it as true, so which means that a start and end and any other special tokens in case the word has to be split, it will automatically provide provision for that. Truncation, yeah. So if the length of the text exceeds 512, so we'll truncate, we'll do the padding to the max length. So if anything is less than 512, say 300, then 212 of the additional digits will be, or the tokens will be generated, and they will be all marked 0. The max length, we already defined it to be 512. Now, if we see the encoder plus, this gives us a dict, right? So when you do or run the encoder plus on the sample, right, you'll find the dict or a dictionary which will have the keys like input IDs, token type IDs, and the attention mask. And now this we need to convert into a D type of torch.long and put them into the tensors, right? So that's what we are trying to do here. We get the input IDs and we convert them into the torch tensors, and so essentially from this tokenized, which is again a dictionary, we get the input IDs. This particular key is being taken and we convert this into the values into a D type of torch.log. Similarly, for token type IDs and the attention mask, we convert them into the torch.log. Now, in case my data is test data, if self dot is test is equal to true, then I just need inputs because it will not carry any labels, right? We need to predict or get the labels identified for the test, so it will not have any labels. So that's why if self dot is test is equal to true, it just needs to return the inputs. So I just need the this part for the test data. But then in case it's not true, it's a false, then we need to look for the label because then it means that it's part of a training data. So label is equal to self.df.loc idx self.classes. So for each of the classes, we get the value or get the corresponding value, and then we put them into a list, right? So it will give me a list of the values for each of the row under the df, right? And for each of the classes. So essentially a list like 3, 3.5, 4, 2, depending upon the values for each of the row item. That's what this will give us. Now again, this label has to be converted into torch tensors. So we convert them to a D type of float 32 and get them as the tensors. Now, in this case, like I stated earlier, we get the inputs or we get a return of inputs and the targets, right? So I have my the features available, which are nothing but the inputs and nothing but these inputs rather. And I also have the labels, which are nothing but this target, right? Then we define the length. So for how many iterations this has to run, so it has to run essentially to the length of the data frame, and that's what we define here, def length self, and it should return the length of the self.df, right? So which will give me the length of the data frame. Now, with this class now, or the feedback dataset class now been defined, now let's get into the train and the validation DF, right? So we do the train test split, and we split this train data in the size of 80 to 20, and that's why we have a test size of 20%, and we give it a random state. So if we have to reproduce the result, and that's why it's important, we can give it any random state, and might be for the different states, the values or the results might actually differ. We say the shuffle is equal to true, which means that every time the data will be shuffled, and that's how your corpus for train and test will be built. Now we take a print of the shapes. So it says it has got 3128 of the rows, the train DF and the validation DF has got a shape of 783, and both have got a number of columns as 8, which is fine. Now let's in the next step. Now we need to okay. So let's run this. Let's run this. Okay. Now in this step, we now need to convert this into the form in which the model would accept the data. So we earlier created the feedback dataset class. So we get the dataset class dataset, right? Or the input and output dataset as input dataset as would be accepted by the model. So okay, so I've not yet run the config. So let me run this, and we come back here and we run this. Oh my god, so I'm still not run the tokenizer. So in this case, okay, so I've forgotten to mention the tokenizer. So we'll define that tokenizer, and we'll so the tokenizer in this case would be auto tokenizer, and uh, dot from pre-trained, right? From pre-trained, and we'll put this as config, and then this is what we need. Okay, auto tokenizer from pre-trained config model. Okay, so we'll run this. So it will be downloading. If it is not there on your notebook, then it will be downloading the tokenizer for the first time. And so now that it's been loaded, so now we can actually run this. Okay, we'll come back to this. And now my train DS, val DS, and all those things are all set. So I can run this as well to see how it looks. So it gives me the feedback data set, right, with the specific ID or memory location where it is kept. Okay, so now we will now do the train loader. So essentially, now that we have defined the format in which the data set will be accepted, Torch provides us the utility to load this data into the Torch, right? So this for the train to load the train, now we can provide train underscore ds as the input. The batch size, we already defined that under config, right? This being a value of 16. Shuffle is equal to 2. There will be 2 workers, and I can pin memory, which happens to be true. So we'll define the same thing for train loader and the validation loader. Now my data, on the data side, we are all set, right? My torch is all set to accept my data. The data now can be run through the model that we might be building. Now let's come to the feedback model here. So the next step, as we discussed earlier in the presentation, is now to define the model architecture. And for that purposes, let's create a class called feedback model and let it inherit the properties of an dot module, right? So it inherits the properties of an dot module here. Now we'll initialize it, and we pass on the arguments like config, and in this case there are 6 different classes for which the predictions has to be done. Okay, then we have the inheritance part of it, and In this case, the model name, we need to provide the model name, the encoder, the dropout, right? So in this case, the model is essentially the BERT base and case that we defined earlier under the config. The encoder is essentially then the auto model dot from pre-trained self dot model name. So and then across the various hidden layers, we want to have the dropouts. As we discussed earlier, the fully connected layer. There are two FC1s, fully connected layers. So we'll define the forward propagation step here. So we provide the inputs as the argument here, right? So and then self dot encoder, and this will encode the in the inputs, right? And then for each of the output that we get, we'll define the dropouts. So in this case, uh, right now we have defined the dropout to be 0. Then the output has to be then passed through the fully connected layer, the FC first fully connected layer, and then the second fully connected layer, and this is my final output. Okay, so this is how the architecture, the model architecture looks like, where we are having the two fully connected layers with 64 nodes, and then eventually the 6 nodes, right? And now with all these things said, now we need to have the trainer function or trainer class through which we can have the forward and the backward propagation done, and get the optimized weights, which will be stored as the model weights, right, as a JSON. Right, so that was it for this video session. Hope you liked it. We'll be soon coming up with the second session in the series, and which will essentially delve into the trainer part of it, and then the third one, which will be the inference part of it. Thanks.